For trial 1, we first enabled the PDP filter in order to turn on PDP mode Glide Auto. Glide produces a smooth position output by fusing information from both the satellites and correction signals to reduce jumps and inconsistencies. After, we used log PDP pos A and log PDP vel A with ontime 1 in order to track the latitude, longitude, altitude, and horizontal velocities of our path every second. While collecting the data, we also held the surveying pole high up in order to minimize any multipath signal scatterings that could be potentially caused by the buildings we were walking around. As a result, our raw data was extremely smooth.
Analyzing the string of characters and numbers that the receiver was returning every second in ASCII. This included the log functions of PDP pos A, PDP vel A. Further research, we found out that some of these values hold the latitude, longitude, and altitude. And so that's what our read function is doing here. It's reading line by line, checking if it's the pos A or the vel A, which means the position log or the velocity log. And then for the position log, it's storing the latitude, longitude, and altitude for each position into its own 2D array. For the velocity, it is kind of doing the same thing, but it's taking horizontal velocity, and that's the only velocity we'll ever really use, and storing that in an array as well. So that's most of where our processing data goes towards. Based on our position and velocity data, we wanted to create a 3D graph of our path, and to further apply it to the real world, we wanted to create a 2D map of our path on Google Maps.
To overlay our path data onto Google Maps, we didn't use a Google Maps API since those can cost money. Instead, we developed a clever workaround where the latitudes and longitudes are directly put into the Google Maps URL through this function. For example, if I select 1, which opens up the Google Maps visualization, we can see our path all because of these imported latitudes and longitudes into this URL.
By choosing option 2 from the program, we can also generate 3 3D plots as opposed to the previous 2D plot on Google Maps. The first plot generated focuses on visualizing the raw trajectory data. To generate our 3D graph, the function takes a list of XYZ coordinates generated from converting geodetic to Cartesian, and then extracts the XYZ values into separate lists. It then creates a 3D plot using matplotlib's functionality, and the trajectory is plotted as a faint blue line connecting the points, and the individual points are overlaid as green dots. Finally, the graph is saved as a PNG. For post-processing, we stumbled upon the Savitsky-Golay filter, which is a mathematical tool to smoothen out noisy data while preserving the shape of the trajectory. Luckily for us, several Python modules allow for easy implementation such as SciPy. Within our code, we created a function that applies this filter to the x, y, and z coordinates separately. In addition, the filter primarily depends on 2 parameters, window length and polynomial order. For our data, we tried several different values for the window length, found that the window length 21 and polynomial order of 3 smoothens out abrupt edges while still accurately maintaining the path followed. Once the data is smoothened, the function creates a 3D plot and is plotted on this blue line, which you can also interact with here. This smoothened plot helps us see the underlying trend in the trajectory by removing noise. However, compared with the raw data, the Savitsky-Golay smoothing only affects the shape by a minuscule amount, meaning that our pre-processed data was highly accurate utilizing the time smooth positions or PDP mode when gathering data. Similarly, this figure is saved as PNG. The third plot creates a velocity colored scatter plot. Essentially, the function uses the original XYZ coordinates but colors each point based on its corresponding velocity at that time. From the matplotlib repository, we chose plasma as our sequential color map, and then a color bar is added to the plot to show the velocity scale for the user. This plot helps us visualize how velocity changes along the trajectory, making it easier to correlate instances and identify patterns or anomalies. Again, this figure is interactable, and it is saved as a PNG.